Welcome back. We're going to be starting chapter 10. We have now entered into the last little push, if you will, of this class with chapters 10 and 11. Today we're going to talk about chapter 10, chemical bonding 1, the Lewis model. We're going to talk about the Lewis model really explicitly in this chapter. In the next chapter, we're going to talk about things like how we know the shapes of these different compounds. We're going to talk about other bonding models as well. So let's go ahead and start on chapter 10. So we're going to be looking at the Lewis model of chemical bonding. And the way what this uses is it utilizes what's known as Lewis models to depict compounds and atoms, right? Named after Lewis here. Like we said in lab, we will be talking about Lewis acids and bases. And we'll see that his model is really the basis for that. Couple things that we're going to realize with these models is one is we're going to use dots to denote valence electrons. Remember, valence electrons are those non-core electrons that are on the outside that are available to do chemistry with. And then what we're going to start doing then is we're going to be able to draw what's known as a Lewis electron-dot structure. One of the things why we need to learn this, one is because we need to know the shape of compounds, because it's very important to know the shape. We need to know how things are bound together, so then we can know the shape. And we need to know the shape for a variety of different downstream applications. But it's also very predictive, right? There's power in this model, predictive power. And what I mean by that is we can now start to answer the question why it's H2O and not H3O, and why it's NaCl and not NaCl2. Right. And again, like we also said, it also kind of points us towards the shape of the compound, but we need to know this before we can move on to chapter 11 to start talking about shapes and how these compounds look. And so let's look, there are three major types of chemical bonds. Ionic bonds, we talked about where there is a physical electron transfer from one element to another, causing two ions, and then they come together to become electrically neutral. There are covalent bonds. We're going to talk about which are usually between two nonmetals, like we said, where the electrons are shared between two elements. We'll talk about the equivalent sharing and how some ionic or covalent compounds are not shared. The electrons aren't shared evenly. And then we have metallic compounds where the electrons are actually pooled in what's known as an electron sea. As we see here, this will be at the very end of the chapter. We'll touch maybe just briefly on it. We're really going to focus on ionic compounds and covalent or ionic bonds and covalent bonds. So let's talk about drawing Lewis structures. One of the things that we're going to talk about when we talk about Lewis structures is what's known as the Lewis symbol. And the Lewis symbol represents the valence electrons surrounding main group elements. Right. And the way, again, we do it with the Lewis structure, with the Lewis model, is we use dots to denote valence electrons. And so what we're going to do is we're going to go to the board real quick. There we go. Let's go to the board and let's just look at why we care, or the quick way for us to easily draw Lewis dot structures. And this harkens back to your periodic table. So again, we're talking about main group elements. Remember, those are the things that are not in the middle, transition metals. Everything else is main group. And we know we have columns here, right? So you have 1, 2, 3, 4, 5, 6, 7, 8. Right? And so in your periodic table, let's say we have sodium, right? Calcium, nitrogen, let's say chlorine. Actually, I think nitrogen is 5. We'll just do chlorine. Ones that I know right off the top of my head. So, right? And what we know is how many valence electrons does sodium have? Sodium has 1 valence electron, so we denote that with a dot. Sodium has 1. So what do you think? How many valence electrons does everybody in this column have? Or alkali metals, right? That's right. They have 1. Calcium has 2. Chlorine has 7. Right, and we're going to come back to this in a little bit, but what we see is that the column with which each of these elements is found, that denotes the number of valence electrons they have, which then we could easily then draw the Lewis structure for each of these elements. Now the question arises, what's the goal, right? What's the goal when we talk about doing these models, when we talk about binding things? What's the goal? And so let's go ahead and go to the PowerPoint slide. And so here is the goal. The goal is to get what's known as an octet, right? It's to get an octet, which is, you know, the most stable conformation of electrons in an element, right? And where do you think we find things that have octets? Exactly, in the noble gases. The noble gases have octets. And so everything is trying to get to a noble gas configuration, right, with a complete octet. And that is why we know potassium, we know those alkali metals and those halogens are violently reactive, because they want to get just one extra, they either want to lose the electron or gain an electron to get to the noble gas. Now there are 2 exceptions, and that's known as a duet. So hydrogen and helium are the exception when it comes to getting an octet. Hydrogen cannot have an octet. Hydrogen can only have 2 electrons. Same thing with helium. They only have 2. To be honest, if I were to have you draw Lewis dot structures, it's the placement themselves of the dots is not necessarily important. I draw mine a specific way, and I'll show you why. But it's just really the amount, right? Just make sure that if something has 6, you need to put 6 around it. So the Lewis model, as we'll see, can model ionic bonds. However, this is not where its strength is found in, but we can still look at it. So what we can see here, right, is that there's an octet in the previous level, right? If we were to do the noble gas configuration of potassium, you would do that with a 4s1 just left over. And so obviously potassium is going to lose 1 electron. But let's look at how we can use this for maybe predicting ionic compounds. Now you guys have memorized, rightfully so, that sodium is always +1, calcium is always +2, things like that. But now we're going to look at why. And it has to do with valence electrons. So let's look at calcium and chlorine, right? So I'm going to redraw these. So we have calcium, right? We say calcium has 2 valence electrons. And we're going to add it to chlorine, which has 7. Remember, the end goal of these elements, what they would like to see is an octet. Well, how do we fulfill an octet between calcium and chlorine? That's exactly right. We would take one of those, right? Because a metal, we said, freely gives up its electron to the non-metal. And so it's going to give up that electron into the chlorine. And so now we have a chlorine. I'm just going to redraw this one right here. We have a chlorine with 8. It's happy. Is the calcium happy? You're right, because it still has 1 more to give. And so what we need to do is we need to add another chlorine. And with 7, this one is going to come in, fill the void. And so now what we have done, right, because again, we've added an electron to these chlorines. So they are going to become -1. We've lost 2 electrons from this calcium. It's going to become +2. So what is the molecular formula for calcium chloride? CaCl2. Right? And so this is how we can use the Lewis model, Lewis dot structures, to help predict ionic compounds and what ionic compounds will be formed. But like we said earlier, it's not, this is not the strength of the Lewis model. We will see the strength in the Lewis model coming up. So let's go ahead and keep going here with ionic compounds. And so formation of an ionic compound is not just dependent on its constituent ions. What I mean by that is it's not just, you know, in the example on the slide, sodium +1, chlorine -1, just coming together, and boom, you got a salt, right? You got this ionic compound. There is some extra stuff to it. And what I mean by extra stuff to it is if we were to just take Na+1, Cl-1, put them together, it would be very highly endothermic. And if you remember from a couple chapters ago, endothermic reactions require energy to occur. However, if you look at the formation of an ionic compound, it's actually quite exothermic, right? Which means it gives off a lot of energy and a lot of heat. And here's the reason why. And it's the idea of what's known as lattice energy. It's the energy associated with the formation of a crystalline lattice of alternating cations and anions from the gaseous ions. Key right there, gaseous ions. We're going to look at what's known as the Born-Haber cycle on this slide. And what, remember, Hess's law, right? If you have a series of delta H's, you can add them all up to find the delta H of the formation, in this case of an ionic compound. I'm not going to have you guys memorize all of this, right? But you can see the steps that it takes to make sodium chloride. What I do want you to focus on, though, and this is something that you will have to know, or at least be familiar with, maybe not necessarily for an exam, but maybe for the final, is that last step, right? Is that last step where you're putting sodium and chloride together. And the key was in the gaseous state, right? In the gaseous state. And so what you can see is that you have sodium +1 gas plus chloride -1 gas. They come together. That's the exothermic. That's the lattice energy. That's what causes the formation of an ionic compound. And so that's really what we just need to focus on, is that those two ions have to be in the gaseous state. It takes a lot of energy to get there, but then the energy is gained back, if you will, on the formation. We talked about this with Coulomb's law, right? That the size and the charge of ions can have an effect on ionization energy, right? That the larger the ion is, the less negative, right? The lower energy that this lattice energy has. So we're dealing with negative, so it's going to be a little bit backwards. The higher the charge of the ion, the more negative the lattice energy is. And so if you can look at the size, we're looking at chloride ions. And so remember, as we go down a group, we gain in atomic radii. And what you can see from lithium chloride to cesium chloride, you actually are losing, you're becoming more positive in your energy. And then if you were to change the charge, like what we said with Coulomb's law, if you change the charge to +2 and -2 as opposed to +1, -1, you quadruple almost your energy output. And so these are just, again, the same concepts we saw in the last chapter are coming back into this chapter here. So let's talk about Lewis structures, right? Let's talk about Lewis structures with covalent compounds. And what we're going to see is we're going to see a variety of different things. One thing that we're going to talk about is how do we know what is a Lewis structure, what's not a Lewis structure, and then we're going to talk about, well, how can we go about, making a Lewis structure. And so I'm glad you asked all those questions. So let's just start on this. We'll probably do a second video. Actually, I might end this video here. So we'll just do ionic compounds, and now we'll do covalent compounds, and we'll look at covalent compounds and how we make them, and the rules involved in Lewis structures.